Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to chemistry class, chapter 5, liquids. Today, topic under discussion is energetics of phase change, enthalpy change, molar heat of fusion, molar heat of vaporization, molar heat of sublimation, energy change in intermolecular forces, heat of vaporization is greater than heat of fusion, heat of vaporization of iodine is greater than other halogens, and dynamic equilibrium with definitions and examples. First of all, we say that we will discuss energetics of phase change. In matter, there are two types of changes that occur: physical change and chemical change. Both these changes are accompanied by heat uh, absorb, absorption or release of heat content. A physical change is the quantitative measurement of strength of intermolecular forces of attraction. That is, if there are strong intermolecular forces of attractions among atoms or molecules, then more heat is required to bring a change in its physical state or bring any physical change. When a substance undergoes phase change, its temperature remains constant, even though heat is being added. It's very important point that when a phase is changed, that is from solid to liquid, heat is continuously supplied, but temperature remains constant. Then where that heat goes? Actually, the supplied heat is used in conversion of phase, either from solid to liquid or from liquid to gas or from solid to direct gas phase. That added heat is used to change the phase of the metal, to change the state of the metal. That is from solid to liquid or liquid to solid and many others. Now, the next is enthalpy change. Enthalpy change is basically the energy change of a system at constant pressure. At constant pressure, the energy change is known as enthalpy change of the system. Enthalpy change is denoted by del H and it is expressed in units kilojoule per mole. Now we will discuss molar heat of fusion. Molar heat of fusion is basically amount of heat that is required to convert 1 mole of solid into liquid state at its melting and vice versa. This is molar heat of fusion. It is denoted by del HF and measured in kilojoule per mole. Let's see, we have ice and definitely it is water in solid form. When we will supply heat of 6.02 kilojoule per mole, this solid form of water is changed into water liquid form and vice versa. When you will bring the opposite change, that is from liquid water to solid ice, that energy is removed to the system, that is energy is removed. The next is molar heat of vaporization. Amount of heat required to convert 1 mole of liquid into its vapor state at its boiling point is called molar heat of vaporization. That is simply, you have to convert liquid into its vapor state, and that should occur at its boiling point. This is molar heat of vaporization. This is denoted by del HV and it is expressed in kilojoule per mole. For example, water is in liquid form. We supply 40.67 kilojoule per mole of energy and now it is converted into vapor form. And this occurs definitely at its boiling point, that is 100 degrees centigrade, and also vice versa. That is from water vapor to liquid form. That energy accompanied is known as molar heat of vaporization. Next is molar heat of sublimation. The amount of heat absorbed to sublime 1 mole of solid into its vapor state at a particular temperature at 1 atmospheric pressure is called molar heat of sublimation. That is, now there is a conversion from solid to direct gas without exempting the intermediate liquid form. A solid is directly converted into liquid form, into gas form. Definitely, in that, more energy is required. It will absorb more and more energy from conversion of solid to direct gas state. It is denoted by del Hs and measured in kilojoule per mole. Iodine is a substance that is a solid that can easily sublime, that is I2 solid. Iodine in solid form can be converted into iodine in vapor or gaseous state. In this, del H sublimation will be 41.08 kilojoule per mole. Now, the next topic is energy changes and intermolecular phases. That is, when we have different forms of matter, solid, liquid, and gas, they all have different types of intermolecular forces of attraction, and definitely when they interconvert with other phases, energy changes will be different. Energy required to convert solid to liquid and liquid to gas will be different. That is, latent heat of fusion, vaporization, and sublimation all involve heat to change the substance. And definitely here no temperature will change because the supplied energy is used to convert the phase of the matter. In case of latent heat of fusion, heat required to change a substance from solid into liquid. Latent heat of vaporization is the amount of heat that is required to change a substance from liquid to gas, and sublimation is amount of heat required to change a phase from solid to direct gas phase. Now, what changes are occurring at the molecular level? Actually, in solids, molecules are very closely packed and very close to each other, and attraction between molecules are very great. This means molecules in a solid structure have very little freedom to move. That is, they have restricted motion. They cannot move freely. They cannot move easily, such as in case of ice. In liquid, molecules are not as closely packed as solid and they have more freedom to move, and intermolecular forces are weaker than the solid. That is the reason that liquid can flow easily but solid cannot flow. In gases, molecules are moving freely as they have very, very weak intermolecular forces of attraction and very large distance among one molecule to the other molecule. That is, there is large distance between atoms or in a gas phase. Now, we will see why heat of vaporization is much greater than heat of fusion. Actually, during melting phenomena, what is melting? Conversion of solid to liquid is melting process. During melting phenomena, a very small change in intermolecular distance and potential energy takes place. But during vaporization of liquid, sorry, here is a typing error. During vaporization, it is not evaporation, it is vaporization. During vaporization, there is a large change in intermolecular distance and potential energy between atoms, molecules, and ions. So heat of vaporization is greater than heat of fusion. We can show it by taking examples with their delta H fusion and del H of vaporization. Like water have melting point 0 degree centigrade, boiling point 100 degree centigrade, and it have del HF with 6.0 kilojoule per mole, and vaporization is 40.7. You can see that del H vaporization or heat of vaporization of water is greater than its heat of fusion. Same the reason that we have discussed in the previous slide, that during vaporization, a large change in intermolecular distance and potential energy takes place. Same, you can compare the data from the other examples like ethanol 7.61 and 26, in methane 0.9 and 8.18, and so on. Now, the next is why heat of vaporization or heat of fusion of water is greater than ammonia and carbon dioxide. First of all, we will tabulate our data for these three compounds. Del HF for water at 273.15 Kelvin is 6.02 kilojoule per mole. For ammonia at 195.4 Kelvin, del HF is 6.652 kilojoule per mole. And for carbon dioxide at 217.0 Kelvin, del HF is 8.33 kilojoule. Now, see its del HV value. Water at 373.15 Kelvin has del HV of 40.6. Ammonia at 239 Kelvin has del HV of 23.35. Carbon dioxide at 194.5 Kelvin has del HV of 25.23 kilojoule per mole. Now, we will compare that data. Actually, water is very strong polar compound, that very strong polar nature. Definitely, it has strong intermolecular forces of attractions, and especially hydrogen bonding. A single water molecule can make two hydrogen bonds, as oxygen has two lone pair, and water can use all these two lone pairs of oxygen in making hydrogen bond with the neighboring atoms. That is, a single water molecule can make two hydrogen bonds. Now come towards ammonia. Ammonia NH3 is again a polar nature, has a polar nature, and have strong intermolecular forces. That is hydrogen bonding. But hydrogen bonding in ammonia is not as much strong as in water, because in ammonia, nitrogen has one lone pair, and it can use only that one lone pair in making hydrogen bond. That is, ammonia can make only one hydrogen bond per molecule. Come towards carbon dioxide. Carbon dioxide is non-polar compound and definitely have weak intermolecular forces of attraction as compared to water and ammonia. So, from this discussion, we can conclude that del HV of water is greater than ammonia, which in turn is greater than carbon dioxide, and same for heat of fusion of water is greater than ammonia, which in turn is greater than carbon dioxide. Next question is, why heat of sublimation of iodine is much greater than other halogens? You know that halogens are fluorine, chlorine, bromine, and iodine. Iodine is volatile solid, that is, it can easily change from solid to liquid phase, from solid to liquid and liquid to gas phase. Its del HS is 41.80 kilojoule per mole at 480 458.4 Kelvin. Iodine has highest heat of vaporization than other halogens. Like we can show the data, del HB for fluorine at 85 Kelvin is 3.16 kilojoule. Fluorine at 239.1 Kelvin showed 20.21 del HB. Bromine at 332.4 Kelvin have del HB of 29.4 kilojoule per mole. Iodine at 85 Kelvin has del HB of 41.57 kilojoule per mole. From this data, you can see that iodine has maximum del HB value as compared to fluorine, chlorine, bromine. Why is this so? Actually, iodine is the last member of halogen family. As we move down the group, atomic size is definitely increases. That increase the polarizability. Because of polarizability, intermolecular forces, that is London dispersion forces among iodine molecules becomes more and more strong or increase. As these London dispersion forces increases, iodine has more del del HV value than fluorine, chlorine, and bromine. The next is dynamic equilibrium. Dynamic equilibrium is basically a state of reaction in which forward reaction is exactly equal to the reverse reaction or to the backward reaction in the same rate with no change in the system. That is, forward reaction and backward reactions are occurring simultaneously at the same pace, and there is no observable net change in the system. That is, we can say reaction is continuously proceeding in both backward and reverse direction dynamically, but there is no net change in the amount of product or either the reactant. Dynamic equilibrium is called steady state. At dynamic equilibrium, both reactions, forward reaction and backward reaction, are occurring simultaneously at equal pace. For example, acetic acid undergoes dissociation and it produces hydrogen ion and acetate. In the state of dynamic equilibrium, these both reactions are equal. That is, acid molecules are ionizing and these ionized ions again unite to form the acetic acid. These both reactions occur simultaneously. This reaction is shown by this form. That is half arrows, one in the forward direction and other in the backward direction. Similarly, we can see dynamic equilibrium when NO2 molecule dimered to form N2O4. Again, at this state of equilibrium, that is dynamic equilibrium, rate of forward reaction is equal to rate of backward reaction. That is, when two molecules of NO2 produce N2O4, at the same time that one N2O4 dissociate to produce two NO2 molecule, and there is a dynamic equilibrium in that system. The next is the synthesis of ammonia via Haber process. In this, the reaction is nitrogen plus hydrogen gives you ammonia. At dynamic equilibrium phase, rate of forward reaction, that is production of ammonia, is exactly equal to the dissociation of ammonia to produce nitrogen and hydrogen gases. And other is at 0 degree centigrade, ice in solid form exists with water in liquid form. that is at 0 degree centigrade, these both phases exist simultaneously and a rate of forward reaction equal to the rate of backward reaction. Thank you. I hope you have enjoyed today's lecture. Now there is an assignment for you. When a substance undergoes phase change, its temperature remains constant even though heat is being added. Why? How will you explain dynamic equilibrium between two physical states? Heat of sublimation of a substance is greater than heat of vaporization of that substance. Support the statement by quoting example. Why heat of vaporization of water is much greater than carbon dioxide? This question can be why heat of vaporization or why heat of fusion. Here is why heat of vaporization. Thank you. I hope you have enjoyed today's lecture. Thank you and have a nice day.